Let's examine heap sort. Heap sort is one of our efficient sorting algorithms. Its big O is n log n with respect to time. And this is a comparison-based in-place algorithm. That means that its space efficiency is also order n. And the order of the final sorted elements is selected by choosing either a min heap or a max heap. For an ascending order sort, we will use a max heap and we will remove the largest element from the heap and place it as the last element in the array, and then we will restore the heap order property in the heap and then rinse and repeat by placing the next largest item in front of the item we just placed, etc., until we have a sorted array. So to do this, we use a two-step process. We begin with an unsorted non-heap array, and the first thing we do is we heapify it. So in this case, we'll cover an ascending order sort. So we will heapify it into a max heap. And then the second phase begins by our continually dequeuing the largest item and inserting it into the sorted array at the end of the sorted array, and then restoring the heap order property, and then carrying out the next dequeue until the heap portion of the array is empty and all we have is the sorted array. So the idea here is that we're going to be sharing space. We initially begin with something with an array that is not a heap at all, and then we heapify it, and now the array is fully a heap. And then we will begin by taking one item at a time and splitting the array into a heap portion and a sorted array portion. And after this entire algorithm is carried out, then the array is sorted. The example that we will use is an ascending order sort. So this is basically saying more of the same thing, and that is that while we can place these elements in different containers, there's no need to do so. This is an in-place sorting algorithm. So in nearly all cases, when you implement heap sort, you will implement it to share the space, and then to just subdivide those n elements of the array into some part of it containing the heap and the other part of it containing the sorted array. Once again, we will make that clear in the example that we go over. Here is an implementation of heap sort. So what you see there is that that first for loop is the heapify loop. Okay, it goes from halfway into the array, which is that's the first node that has children, and then it heaps that node down and then decrements all the way to the root. So this is a loop that moves backward. It moves from n over 2 minus 1 all the way to 0 and heaps down each one of the elements. Once the array is heapified, we then enter that second for loop, which is actually what does the sorting. It begins at the end of the array, as you can see there, at element n minus 1, and decrements all the way to index 1. And the reason it doesn't go all the way to 0 is because when we're down to a single element, that element is in fact sorted by itself, and so it's just and it's already in place, so there's no need to do any work. So what we do here is that we go from the end, we swap. You notice that I is my variable, and we swap the data 0, which is the element at the top of the array, which when it's in heap form, that is the highest priority element, which means it's the maximum element in a max heap. And we swap that with the data item, and then we restore the heap property of the, we perform a heap down all the way to the I-1 element, which means that we have now, we no longer consider the last element part of the heap. So when I go over an example, this will hopefully make a little bit more sense. But while we're at this implementation, it's a good time to talk about the efficiency of this particular algorithm. So this is a pure n log n algorithm, and it is n log n in all cases, in the best, average, and worst case. And the reason for that, hopefully you can see that that second loop goes from n-1 all the way down to n. In essence, that is a loop that is order n. But that loop, so that this loop, the bottom loop here, this loop goes through pretty much everything in the array. It goes from the last element all the way to the next to first element. In essence, that's order n. So why is this not an order n algorithm? Why is it an n log n algorithm? That's because of this heap down that's happening in possibly all n cases. If you'll remember, the heap is a complete binary tree. And as a complete binary tree, the height of that tree is log of n. When I heap something down, I may have to heap it all the way down from the root all the way to the leaf. Therefore, I've got n out here, and I'm doing log n work in here, and that log n is happening inside of the loop. So therefore, this is an n log n algorithm. Now let's take a look at the example. So let's take a look at this example. Let's just look at some nomenclature first, and let's focus on one image at a time. So to point out how everything is laid out here, the vertical bar that you see in the subblocks labeled array, that is showing the array container. And that vertical bar splits the array into the heap portion, which decreases in size by 1 each time, and the sorted array portion, which increases in size by 1 each time. And so we begin with an array that is neither sorted nor is it a max heap in this case. So that is what you see at location 1. And we begin with that array, and the first thing we must do is to heapify it. Remember, to heapify, we will begin by going to the first node that has children, and then going all the way to the root. So in this case, the size of this is there are 5 nodes, and so this is the halfway point. And so heaping down to 12, since this is a max Q and 18 is greater than the 12, I'll redraw it here. So the 4 is going to remain at the top, but the 18 and the 12 are going to swap places. This is a heap down. The 12 goes here. And then the other side remains untouched. Okay. and we have heaped down the 12 as far as it can go. It's now a leaf, so we terminate that iteration and we decrement. We were at index 1. Remember, this is index 0, index 1, index 2, so on. We were at index 1. We've heaped down that index, so we now decrement and we're at the root. Let's heap down the root. So that begins by looking, so the root is 4, and so we compare it to 18 and 6, and both 18 and 6 are greater than the 4, so we pick the larger one and we swap. And so we've got the 18 here, and the 4 now is here, and the 6 is here, and then the 3 is here, and the 12 is here. Remember, we're not done heaping down until we no longer violate the heap order property or we're at one of the leaves. In this case, we're still violating the heap order property because the 12 is in fact greater than or equal to the 4, so we will heap the 4 down, and then that tree looks like the 18 stays at the top, the 6 stays there, and the 12 comes over here, the 3, and then finally the 4. And if you notice, this particular depiction of the heap is what we have here. Okay, so we are now in heap form. Let's just confirm that the 18 is greater than both the 12 and the 6, and the 12 is greater than both the 3 and the 4. So we are now a max heap, and we can begin the process. So we begin the process by swapping the 4 with the 18. So we remove in essence, we're removing this, but we do it by swapping the first element and the last element. So our array looks like this now. And when we effect this swap, okay, when we do this, then you notice that the 18 is now at the end of the array in number 3. So what happens here is that this is gone from the heap, and the 4 is now up here, because you notice that we decrement the size of the heap to only be now 4 nodes. Okay, and this 4 needs to be heaped down. Okay, so the 12 is greater than or equal to 4, and the 6 is greater than or equal to the 4. 12 is the greater child, so we pick that, and we move then the 4 here, and we move the 12 up here, giving us the diagram on the right. So the 12, the 4, the 6, and the 3. And you notice that now looking at image 3, that we have now decremented the size of the heap by 1. Initially we had 5 elements in the heap. We now have 4 elements in the heap and 1 element in the sorted array. Okay, so the next step then is to swap the root with the last item. Okay, so that we swap the 3 and the root, and then we decrement the size of the heap. So this guy is gone, and this guy is now a 3. Okay, and we have to heap down the 3. Well, both the 4 and the 6 are greater than or equal to the 3, so we'll take the greater of those, which is the 6. We heap this down. And the 3 ends up here. And now, you notice when we swap this 12 and the 3, the 12 is now in the sorted portion. And the array, the heap side, looks like 6, 4, and 3. There's the 6, there's the 4, and then there's the 3. And you notice that the in green portion, that array is sorted. That sub part of the array is sorted. Okay, here we are. We're going to now, we're in step 4. We're going to swap the 3 and the 6. Okay, so when we do that, I'll do it in this picture and that'll link us to this picture. So this becomes the 3. This now is completely removed. Okay, and the 3 needs to be heaped down. The 4 is greater than or equal to the 3. So we swap these two, giving us then a 4 here and the 3 here. And you notice that that's what's in this picture. And you notice that we move the 6 into in the front of the sorted portion, and we now have a heap of size 2 and a sorted array of size 3. Okay, last element, because once we get down to one item, that item is sorted. So this last one is to swap the 3 and the 4. Okay, that really means put the 3 here and get rid of the 4 because we're moving it into the sorted portion of the array. Okay, so at this point we're down to a single element in our heap, and that's going to be sorted. So when we affected this switch by moving the 3 and the 4 became part of the sorted array. Okay, and now we're down to just one element, the 3. We basically leave it in place. We decrement the size of the heap. So the size of the heap is now 0, and the size of the sorted array is now 5. And if you'll take a look, it's 3, 4, 6, 12, 18. That is an ascending order sort.